Swayam Prabha. Digital India. Educated India.
Good morning, gentlemen. We have been talking about the static equilibrium, and in the last class we talked about the static equilibrium, various equations of one single rigid body. So what we have done is that if this is and if this is a rigid body acted upon by a number of forces, so what we have derived is that the equilibrium equations, this is from a single point to a starting from a single point, that means that equilibrium of a particle, and then from that we integrated it to the equilibrium of a rigid body. And for equilibrium, so we said that it is sigma Fi is 0 and m is 0 here, moment about 0 here, and this moment can be also a vector, in the sense that the moment can be taken about x, y, z axis. So essentially, if you have a body under equilibrium, so we said that the total Fi, we call it as obviously external forces. All these are external forces, no internal forces, and sigma Fi is 0 as well as sigma m is 0. Okay, in the sense that the moments of all these forces about the various x, y, z axis are is 0. So this can be, for plane, this can be condensed to the sigma fx is 0 and then sigma fy is 0, and moment about z axis is the one which is coming out, so is 0. So that is 3 equations in the case of 2D. So this is 6 equations, 6 scalar equations in 3D, and then it will be 3 equations in 2D, in the sense that sigma fx is 0, sigma fy is 0, and moment about some point we said mg to start with, you remember. So we did this starting from equilibrium equations from a dynamic case, so we came to the moment about z is 0. So these are the 3 equations for 2D, and then after that we also went on to show not only these 3 equations, so this is also equivalent to, or I'll write it right here. So this is in 2D, okay. I'll just continue to write it as I've done last time, is that this is also equivalent to saying sigma fx is 0 and moment about points A and B So A and B can be any two arbitrary points. So if you do this, so sigma fx is 0 and moment about A and moment about B is 0. So that is also equivalent to, so these three are equations are equivalent to this basic fundamental equations. So then we went also on to prove that this is also equivalent to MA is 0, MB is 0, MC is 0. So these are the moments about any three arbitrary points. So let me remove this. Any three arbitrary points about the body or outside the body. So there are a little qualifiers as we talked at length, is that this MA and MB has to be such that this, let me just say that in fact this is also that this fx can even be fx prime also, in fact in any arbitrary direction. So that means that, let me just explain it here. Not necessarily, so we can say that this is x prime, so we can even put it for more generalization fx prime and some point here, and let us say A, and then the B here should not be on a line, so B should not be on this. Should not be on this line. So what is this line? So this line is perpendicular to x prime. So B should not be on a line perpendicular where from A, if you draw a perpendicular to x prime, so if you call it as y prime, so it should not be on y prime. So B should be anywhere else. Okay. We have seen this in detail last time. Y should be so, right? So that's about if you take 2 points A and B together with fx prime, right? On the other hand, here we also have seen that these 3 points A, B, C should not be collinear, that's all, and they should be away from each other. Okay. So that's also is another very important. So C should not be falling on AB line, or B should not be falling on AC, as long as these three are distinctly located, so it is fine. So ABC should not be collinear. Not collinear. Okay, so those are the conditions. So if the body is under equilibrium, either you apply this set of equations or these equations or these equations, they are all equivalent. Okay, so this is the important part of equilibrium equations. So there is also another very important fact here, is that if a body or so if a body is under equilibrium, then any part of the body also will be under equilibrium, and equilibrium in this. So if you have, so this is not only applied to one body, this can also be applied to a system of bodies, multiply connected bodies. So let us talk about that. Okay, so we want to, from this we want to go ahead and apply it to the multiply connected bodies, several bodies connected to each other. Several bodies connected to each other or multiply connected bodies. So connection can be of different kinds. So you will come to know it a little bit later. So for example, we have several bodies. It can be pin connected, they can be resting on each other. Before I take up, let me just continue this a little bit further, saying that there are some very common cases which you come across. So I just want to go back to this one. So there are certain common cases in which we have we come across very often. In fact, to some extent, I think I discussed this in the last class itself, is that if you have body upon by two forces. So this is very often you encounter, and we use this very often in the sense that if you have two forces acting here, so is there any condition? So if these two forces are acting at some points A and B, so if the body is under equilibrium from that equation, first equation, so Fa plus Fb for equilibrium, so this is one thing, which essentially means that Fb is equal and opposite, right? So this is what it says. So that means that to be satisfying the first equation, so Fb has to be, so that means that, so if it has to be, so that means that they're parallel to each other and equal in magnitude. But however, there is also another condition, that the moment has to be zero. Moment of this system has to be zero. So which can be found out that if these two are separated by a distance of d, they are parallel obviously, so there can be a distance of d, and this moment is Fa into, this is all very simple and which you might be aware also. So just for the sake of completeness, I'm doing this simple cases. So which says that if m has to be 0 here, then the distance d has to be 0. Fa cannot be 0, so which means that d has to be 0. So which means that these forces should be such that they are equal and opposite as well as in line. So they are passing each other. So that's only possible. So this is only possible if d has to be 0, and if you know that they are acting at A and B, so the only possibility is that Fa and Fb are along AB itself. So that means that they have to be along. So if you draw a line AB here, so this has to be A, so that means that this is not right, and this is also is not right. So Fa and Fb should be along AB, so that the parallel distance of this Fa and Fb is 0. So that's number one. And then there's also another case where this is quite often what happens is there are cases where we have situation where there are only two forces acting on that, and we know that it's under equilibrium. So we know that they have to be equal and opposite and along the line AB itself. And then there are another case acted upon by three forces. So this also I mentioned in my last class, is that if there are three forces at points A, B, and C, so what we know here is that sigma F is 0, so which means that the first equilibrium condition, that Fa and Fb and Fc, when they added up together, should form 0. So which means that if you have Fa like this and Fb like this, so if this is how these three forces will be there, so they should form a triangle, should form a closed, the force polygon should form a closed force polygon. So here this is true for any cases, so here we say that it's a triangle. And of course this also leads to your Lamis theorem, so I'll just mention it just now. On the other hand, they also should pass through the same point. So the action FAB is the lines of action should pass through same point. So why is this necessary? So that means that if these things are like this, so if Fa and Fb is replaced by, you can transfer the forces Fa and Fb here, and which might Fa and Fb can be replaced by this force here, F prime, and this F prime and together with Fc should keep the body under equilibrium. So we have seen earlier that this and this should be equal and collinear. So that means that this Fc should also pass through this point. So that means that so it is here, but it is at some angle like this one, so that Fc prime should be the line of action, so that it also passes through D. So that is how we can analyze this easily and quickly. So this throws an interesting fact of calculation. So if you know that there are only three forces, so we know that they should pass through this one point, same point, and further, for the sake of calculations, so you can say that they should form a triangle. Or on the other hand, if you transfer Fa and Fb and Fc here, we know that if this is some angle alpha, this is beta, and this is gamma, so we know that from this you transfer it to this one, so we know that this angle is 180 minus alpha, and so on. So we can say your sin alpha okay, so this is your Lamis theorem, right? So this is another convenient way of calculating the equilibrium of these forces. So that way we know that this two force system and a body under equilibrium by three forces are easy to calculate, and in fact this we can make use of it at many places. Okay, so this is how we can analyze one single body under equilibrium. Okay, so now let's look at several bodies connected so that it forms a system of bodies. Okay, this is a system of bodies connected in many ways. So there are many ways. For example, if you have a table here, so this is a very simple system. A table where there's some weight kept here and on top of it, and then there are several bodies. There's a top surface here, top plank, and followed by two legs here, and then it's resting on ground here. There's also, these things are not completely independent, they are connected by pins here. So there is some pin here and a pin between this 1, 2 and 3. 1 is the top plank and 2 and 3 are the cross legs, and 1 and 2 are connected by a pin, and 1 and 3 are connected by a pin, as well as 2 and 3 are connected by a pin or a hinge. So that means that the things can rotate with respect to each other. Okay, so that's how the hinge connection is there. And so this is a system of 3 connected bodies. And also you can consider that there is a ground here. It's also a part of the system. So okay, together they are under equilibrium. Okay, so and then there are many other things which you can also see here. Simple cases. So this is a scissors or pliers. So this is a pliers here which is holding this cylindrical block, and again the 1 and 2 is a curved rods here, curved handles, and then again here these are connected by a pin so that you can hold it any size of the block. So this is another system of 2 connected bodies. So like this we have many, and even you might have seen this is another system of bodies here. Again, there is a cylindrical, hollow cylindrical container. This is a cylindrical container in which there are two balls placed here, and then it's an open container, and it's at the bottom it is resting on the ground here. So this is a system of three bodies again resting on the ground. So like this, so you can have any kind of situations, okay, or the same thing can be continued here. Another small thing. So another system of two rods and with an extra weight here and resting on the ground here by using the pins. Okay, so like this, so we have many places. We have n number of these kind of examples where it's just not one body but several bodies put together for a certain purpose. So here this is a kind of table and which is at a height, so you want to have that kind of thing, and this is the one where you want to hold for several reasons. This cylinder may be hot, or it may even be a nut where you want to crack it by applying some force here, or this is just a tennis balls which is you just put it upside down. Each has its own significance, so we are going to see some of these examples. Now, from the knowledge of this one body under equilibrium, under static equilibrium, so how to apply it to these things? Okay, so we would like to analyze these things for many reasons. So for example, here we have a weight acting on this one. So because of this weight, obviously it has to be transferred to the ground, and so they will pass through these cross legs, and the cross legs as well as the pin here. In fact, pin also can be considered to be another body here, and then everything is subjected to certain loads, and depending upon the kind of weight and depending upon the kind of material it's made of, so each body is subjected to what we call it as stresses. So stresses are nothing but the internal forces, the intensity of internal forces at each and every point. So if the stress is within some allowable value, this is talking about deformable bodies, but if it is rigid, we don't consider that. But however, it's important from the design point of view. So whether each body here can withstand that kind of force. So that's one from the design point of view. Or on the other hand, if you want to look at this one, a pliers with which you apply the force, and then you would like to know how much force you need to apply with on the cylindrical block here. So that means that now the whole system has to be analyzed for the forces and how each body is subjected to what kind of forces here. So there are one important principle here. If the system is under equilibrium, then any part of it is also under equilibrium. Under equilibrium in the sense that the forces which are acting on that are balanced, balanced by those equilibrium equations so that it stays stable. It doesn't move, right? If the force is not balanced, obviously it is going to go have some accelerations and move out. But since the whole system is under equilibrium, so we can say that any sub part of this one, any subsystem, so not only each body here, or maybe you can consider only one top and one leg, or just the two legs. So any subsystem is also under equilibrium. So we are going to make use of that to find out the forces which are coming out on each body. So why do we require this? First one is that, which I said here, is that for the sake of design purpose, we have to know how each body is subjected to what kind of forces, or here we would like to know how much it is, or here we would like to know whether this is stable or not. Okay, you know pretty well that if the dimensions are such that, then there is a possibility that the whole thing can tip also. So we will see these problems a little later. They are all very, very interesting. Each one of them is a very interesting one. So in this context, so what we would like to do is something where we want to bring the concept of free body diagram. So I hope you have understood that the free body diagram is a very important concept of free body diagram is nothing but a diagram or a sketch. It's nothing but a diagram or a sketch or a figure, okay, which will, it's a symbolic representation okay of the body, and structural element or a part of the element in which all connecting pieces are removed. Okay, so that means that there are several bodies here, and then so you can isolate any particular body, okay, and then all its connections are removed. There is also another qualifier immediately which we say, so at those connections, the interaction, the earlier interaction will be shown as an external force and sometimes or moment. So this is a very important part of this. So that means that the free body diagram is that you can isolate any part of this one, okay, or one body or several bodies, and then its connections with all the other connecting bodies is removed, and the interaction of those connections are shown as external forces or agents. Okay, so this is a very important part of our analysis. So what it says is that, so we can take out any part of this, whatever of interest. So here, for example, in this pliers, we can take the cylinder, isolate the cylinder, and then we can show it as an independent isolated body with all the connections removed. So that means that this top handle and bottom handle has been removed, and that earlier interactions. So interaction means that this is holding this one. So since if it is removed, that holding force now is shown as an external force. Okay. So yeah. So I'll continue it here just for the sake of. So for the pliers, for example, you can draw the cylinder here. We can isolate the cylinder. So this, since it is removed from its top and bottom handles, so that force here is shown as external forces on the cylinder. Okay. So similarly here the same thing is true. Now what we can do, interestingly, is that we can consider these two handles as one system. Of course, there's a pin connection here, and then this is now isolated from the cylinder. So if so, then that action of that cylinder on this will be same thing here. So those F1 and F2 are shown here. So this is also under equilibrium. So while this is under equilibrium cylinder, and after removing the cylinder, so these two handles, two tongs with these forces F1 and F2 have to be shown, because this is isolated from the cylinder here, and then this is under equilibrium. Okay. So like this we can also write for many of these things. Okay. And so then some of these interactions are easy to understand, some are a little involved. So let me show you. For example, some simple cases of a cylinder, I mean a block resting on the ground with F like this one. And if you want to isolate this block from the rest of the thing here, is that you have to show the interaction of the ground on the block here. So you know from your earlier analysis, earlier practice of this kind of problems. So if you isolate it, then we know that there is a normal reaction N, as well as there may be a friction, right? So this is a free body diagram again, right? So that is how. And another interesting thing which probably requires a little bit of understanding is the pin. So if you have a pin connection, what kind of internal forces will be there? Once the pin connection has been removed, then the internal forces at the pin have to be shown as external forces on the free body. Okay. And so for example, if you have a pin, so there is a pin here, there's a pin here. So at point A, B and C. So at A, where there is a pin, so cylindrical pin, so we can say that the pin connection, so we have a pin here. So actually you can think that that pin is an additional piece. So there are two rods and with a pin here. So we can consider it to be the pin to be integral of one of the rods, or pin can by itself can be independent. Interestingly, so what are the forces that are coming on the pin? So pin is sitting in a hollow hole like this, right? So what kind of forces you can apply onto the pin by the rod here? So this is the rod. So this is all blown up. So if you understand the forces that can act here, so if there are two surfaces in contact, we know if there is no friction, then the only force that can exist is the normal force. So if you look at the pin here, if you isolate the pin, and at each and every point on the pin, so we assume that there is a contact by this hole in the rod on the pin here. Okay. So if you look at the pin here, so isolate it, what kind of forces you expect here? So the forces which you expect here are the normal forces if there is no friction. If it is a well lubricated pin, we assume that there is no friction and the force is only normal. So the normal means that all those force components are radial. So all of them will pass here through the center, and from the transmissibility of the force from that principle, so all these forces can be transferred to the center, right? So all the forces are concurrent at the center, so they all can be summed up into one single resultant force, right? So that can be put as, so this is the resultant of all F1, F2, F3, right? So that means that either the action of this rod on the pin or the reaction of the pin on the rod, so in any case, so there will be one single force only, and that single force is passing through the center only. Okay, so that means that if there is a pin which is well lubricated without any friction, so then the interaction here will be a resultant force through the center. So the resultant force, I don't know actually the direction, so you can assume that it has Rx and Ry. So you can say that there is Rx here and there is a Ry. You can like it. So essentially there are only two components in x and y direction without any moment. So when is the possibility of moment coming into the picture? So we can also extend this one. If you assume that it is a joint which is not well lubricated, or if it has a friction, so what will happen? So what will happen is that there will be forces, tangential forces. So if there is a friction, so there will be a tangential forces, so which will lead to a moment. So if you take it moment about center, so if you have a friction, then in addition to this Rx and Ry, you will also have a moment acting at the center. So that means that now if you want to eliminate or draw a free body diagram of these forces here, you can take it anything, so or even this one. So if there is we know that this is a pin connection, and if you want to isolate it, so what we can do is that if you want to isolate one, so if you want to continue to write the free body diagram of the handle 1. So what is that? There is a force F1 here. There is of course a applied force by the gripping action, and then here, so if we are isolating this one, so if it is a well lubricated pin, so we can say that there is only one force. So force is radial, and it passes through that without any moment. So if it is without any friction, so we can say that, so Fx, Fy. So these are Fx and Fy are the internal forces at the pin. Okay, so this is how the pin can be isolated from the connecting bodies there. So this is a pin is very important. So pin, if it is well lubricated, then all the forces have to be radial. There is no chance of any tangential force which is leading to the moment, and all these radial forces can be transferred to the center and without any moment, and then it's equivalent to some random force or at some angle, or you can say that it's Rx and Ry with two components like this one. So like this you can write down. So in fact we can even solve this one very easily here. So for example, under the action of these forces, if you want to apply the equilibrium here, you can see that, so all the forces are essentially vertical except this horizontal force Fx. So we can say that Fx is 0. Okay, so we can very easily say that this has to be 0 because that's only the horizontal component. And then now if you have F that's being applied here, and if you want to calculate F1 here, so what is that which you can do? So it's very easy. So it's very simple to calculate it here. So if you think that this distance is d1 and this is d2, and so you can very easily see that if you take the moment about C here, so this is A, C and D. So we can take the moment about C and we can say that F1 D1 is F into D2. Okay, so this is a very simple problem. You would have done it. So I'm just showing it from our approach and show that it can be calculated very easily. So F1 D1 into F2 D2. So why we have done this free body diagram of this one, why it is necessary for these pliers to draw the free body diagram. So that is because if we want to find out what is the gripping force, okay, on the cylinder, so that gripping force is nothing but F1 is equal to F into D2 by D1. Okay, so that is what is the gripping force, and then there is no horizontal force here at the pin. Same thing is true for the top one also, and F1 is the gripping force. Okay, so this is a very simple example of this one, and we will do some other problems tomorrow in the next class. Okay, so I hope you have followed it. Please go through my lecture and you will understand, and if you have it any time later, you can even send a mail to me. Okay, bye bye then.